Okay, guys. So this is chapter 11, section 1. It's going to be a relatively quick section. It's only two definitions and or two theorems rather, and the problems are pretty straightforward. So the first thing they give you is the circumference of a circle. We know that the circumference of a circle is the distance around a circle. There's two equations associated with circumference. The first one is that circumference is equal to pi times the diameter, and the second one is that circumference is equal to pi times the radius. Remember that the radius, I'm sorry, 2 times pi times radius. Remember that the radius is equal to 1/2 times the diameter. Remember that the diameter is the distance completely across the circle. Remember that the radius is the distance from the center of the circle out to the edge of the circle. So that's the first theorem or definition. So there's a couple examples associated with that the book gives. Questions number 1 and 2. So the first question, they say to find the circumference of the circle with the diameter of 5 inches. So since they give me the diameter, that tells me I'm going to use the first of the two equations. Circumference is equal to pi d. So in this case, circumference is equal to pi times 5, and therefore my circumference is going to be approximately 15.71 inches. So that's the first part of number 1. The second part of number 1 is that they give me the circumference and they want me to find the diameter. So using that same equation up here, circumference is equal to pi times d. I can say that 17 is equal to pi times d. Divide both sides by pi, and I get that the diameter is equal to about 5.41 feet. Okay, so that was number 1. We also have for number 2, let's do some definitions for number 2. So first thing they do is they ask us for the distance. So I'm going to say that x is equal to distance. We're going to say that uppercase R is equal to revolution. And then we can say that they give me the diameter of 28 inches. We can say that circumference is pi d, since they give me the diameter. Other stuff that they give us that the car is traveling 500 feet. They tell me that the diameter is 28 inches. Notice that the units are different. In order for us to use this equation, both units have to be the same. So it's easier to convert feet into inches, so I'm going to multiply 500 times 12 and get 6,000 inches. So those are going to be helpful for solving this problem. They want us to find out how many revolutions or how many times the car turns, or the car wheel or the car tire turns after going 6,000 inches. So when I set this up, it's going to be 6,000 equals the number of revolutions, that's what we're looking for, times the circumference, which is in this case pi times 28. So what I'm going to do is I'm going to divide both sides by pi times 28, and I'm going to get that the number of revolutions is going to be approximately 68. Notice that the revolutions is not in any units because all the units cancels out. So you're not going to have any units. So it's going to be 68 revolutions. The next thing the book talks about is that of an arc length. And it says that the arc length is a portion of the circumference of the circle. So we talked about it in chapter 10 using degrees. There are actually two ways to measure arc length. We can measure arc length in units. And what I mean by units, I mean feet, inches, meters. We can also talk about arc length in degrees. And what we did in the last chapter is talk about arc length in degrees. So it says that the arc length is a portion of the circumference of the circle. So since it says it's a portion, portion can mean a fraction. Or we can get a fraction out of it by setting it over the circumference. So there's two ways that the book describes arc length. They call it the, for units, they call it the arc length of. For units, I'm just going to call it arc length in units. So I'm just going to write it like this. When you see that, that means arc length in units, meaning inches, feet, centimeters. And then the book calls the measure of the arc length, we're going to measure that in degrees with the M in front. So when we talk about writing a fraction with these, we're going to do units over units, and degrees over degrees. Let's write DEG. Units over units and degrees over degrees. What does that mean? So we can make, since we have two fractions dealing with arc length over some type of total circumference or some type of total circle, we can make those ratios or fractions equal to each other and form a proportion. In terms of the units over units, we can say that the arc length in units over the circumference, in this case the circumference would be either 2 pi r, or the circumference can be pi d. This arc length in the numerator is measured in units. This arc length in the denominator is measured in units. So that would be units over units. We also can do it in degrees. We can make our fraction in degrees. And we call that the measure of the arc length. In order for us to have a circumference, the circumference is one full circle. One full circle can also be measured in 360 degrees. So the circumference of a circle, 2 pi r or pi d, is equivalent to one revolution or one circle or one distance around a circle, which is 360 degrees, which is why these are equivalent statements. These guys are measured in degrees over degrees, and we can set these two guys equal to each other. So we can say that the arc length in units over the circumference is equal to the arc length in degrees over 360 degrees. So using this proportion, we can maneuver between arc length in units and arc length in degrees, and that is our second equation, or our second corollary in this case. So this would be the arc length corollary. And we learned about arc length in chapter 11. So there's a few examples associated with that. We have, for number 3, we have that a circle, QPS, we have arc length QP, and they want to find the length of QP. Notice that they already give us a degree, 75, so they're asking for the arc length as a unit. So we write our equation. Arc length in degree over 2 pi r. Oh no, they give us the diameter. So since they give us the diameter, it's going to be pi d is equal to the measure of the arc length in degrees over 360. So I'm going to multiply both sides by pi d. So qp So pulling in the numbers for that, since we're looking for QP, that's going to still be there. That's not a P. Is equal to 75 over 360 times pi 9. And I get that the arc length is about 37.7 inches. Yay. For number 4, they want the circumference. So I'm going to write it this way, and they want the arc length of LM in units over circumference is equal to the measure of arc length in degrees over 360. Since the circumference is in the denominator, I'm going to do the inverse of both equations, and I'm going to rename it as circumference over LM is equal to 360 over the measurement of LM. Plugging in the numbers, circumference over 61.26 is equal to 360 over 270. So I'm going to multiply both sides by 61.2. So circumference is equal to 36 over 27 times 61.26. So then I get that my circumference is approximately 81.68 meters. 81.68 meters. Okay. Then we have number 5, which is similar to 4. But in this case, they want us to find the radius. So I'm going to do the same thing like I did before. I'm going to fast forward though and say that the circumference, after inverting both sides, is over 10.5 is equal to 360 over 150. So I skipped some steps. I did the inverses of both equations to get the circumference. So circumference is equal to 36 over 15 times 10.5. So my circumference is going to be 25.2, but this is not what they want me to find. They want me to find the radius. So I know that circumference is equal to 2 pi r. I know that my circumference is 25.2. So I'm going to divide both sides by 2 pi. And I get that my radius is going to be equal to about 4.01. In this case, I believe it's feet. Yeah. So this is a two-part problem. The first part was just like number 4, finding the circumference. So that was part 1. And then part 2, after you find the circumference, divide both sides by 2 pi so that you can get the radius. And I got 4.01 feet. Okay, so for the last question here, they give us this track. They have a guy in black who is running on the outside of the track, and his radius is 44.02 meters. So this equation actually comes really handy. It's the example already. They got distance is equal to 2 times the length of each straight section times 2 times the semicircle. So notice that he's running this portion right here. This is basically a circle, or half of a circle. And since he's running a track, there's the other half. So we have a semicircle and a semicircle. We can add those two guys together and get a whole circle. And then the straight edge is 84.39 meters. So if that's 84 and that's 84, we can add these two guys together, and we can add these two guys together, which is basically the circumference of one circle plus these two lengths to get the distance. So for this guy, to solve, we're going to basically add the two straight sections. So we're going to add the two straight sections. Plus the circle, really. So this is going to be 2 times the 84.39 plus the circle. Now the book says 2 times the semicircle, which is 2 times 1/2 of 2 pi r. Why write 2 times 1/2? We know that it's one whole circle if we add them together. So I will just write it as 2 pi r. So 2 pi, in this case our radius is 44.02. So 2 times 84.39 is 168.78, and then 2 pi times 44.02 gives me about 276.5858.172. I'm just going to write everything. And when I add those guys together, I get about 445. They wanted to round it to the nearest tenth? Yep. 445.4 meters. And that's going to be my distance around one track. So we add the straight edge. Since there's two straights, one here, we multiply it by 2. We have 2 semicircles, but I call it one whole circle since the radius are the same for both. Add those guys up together and you'll get your distance around the track. So those are all the questions associated with 11-1. Hopefully you find this beneficial when doing the homework. Have a great rest of your day, guys. Take care.